Okay. So today is less going to be like presentation. Like I'll present briefly, but it's mostly going to be a work day. The main goals for today are to get like most of the conceptual design of the aircraft. Here, let me find something real fast. Okay. Yeah, so I'll talk a little bit about the models today, and then I'll let you guys loose with it. And then on Thursday, there's also going to be another work day, and there isn't a presentation planned at all for that. It'll just be like working. And then next week on Saturday, although it can be rescheduled depending on your guys's availability and stuff. The plan was to have you guys do like a little presentation on the conceptual design that you guys picked. So keep that in mind, just scheduling wise. Yeah. So, oh my God, I have so much open right now. It's painful. Actually, I'm just gonna share my whole screen. Okay. MATLAB, and just, cool. Okay. Yeah, so this is a sample script that I threw together to kind of show you guys the three main models that we have right now. And so what you guys are going to end up doing is like putting your own parameters and stuff in here to try to calculate the score that you think different designs will get you. And so I guess the first thing I'll do is I'll just run this script. So you can see what it outputs. Sorry. Warning off. That's not the word warning. Yes, I did mean that, MATLAB. Thank you. Okay, that'll just make that not show up. That's a warning inbuilt into our code that is important, but not super important right now. So we're going to ignore it. And so this code immediately generates 4 plots. The first plot is top speed in feet per second. And as we were talking about on Saturday, no, on Thursday, I think, yeah, Thursday. We can use the wing loading and the power loading to calculate the top speed of an aircraft. And so that's what this contour plot shows. This next one shows the takeoff distance, and I'll talk more about that in a second, how we model that. And then this one is the empty weight. Now, this one had a few more assumptions go into it. You do need to also set a takeoff weight on that. You can't just have the wing loading and power loading. But so this one is set to like with a takeoff weight of 5 pounds. This is how much of that would have to be devoted to structures for each of these wing loadings and power loadings. And again, I'll show you guys what the code is that generates that as well. And so you can use this type of thing to generate constraints. And this is another thing we were talking about on Monday. So I put some arbitrary constraints in here just to show you kind of what that looks like. This red constraint is a constraint at 50-second laps, for example. So if you like, our laps have to be shorter than 50 seconds, you can plot a constraint there. And then this one is a constraint at 12 feet takeoff. So that's the blue line here. First, any questions on these charts? Just like what they are, what they represent. I'll talk about how to actually make them in a second, but
you said the blue is 12 feet takeoff?
Yeah, I just picked a random number for that. All right, cool. So the heart of most year's performance code is this function here, this lap calc parabolic wind. And the parabolic means that it uses a parabolic drag polar. That's that drag polar we were talking about that Dr. Drake said is like a fake drag polar or whatever. It's the CL squared over pi EAR. And that's in that presentation from Thursday. And then the wind means that it just accounts for wind. So if you look at the inputs on this function, and also anytime you see a function in this code that you're like, what the hell does that do? Right click open. And so you'll see that this is a function that was mostly written by Nathan and Jared 2 years ago. And the inputs are the wing loading, the power loading, and then the air density, the base propulsion efficiency, the parasitic drag coefficient, the Oswald efficiency, the aspect ratio, the turn CL, ignore beta. I think I got rid of it. Yeah, I got rid of it. Yeah, pretend that doesn't exist. I'll explain what it's for in a second, but for now it's not super necessary. And then you have this wind velocity and this wind angle. And usually we want to plan for the worst case. We've previously demonstrated that the worst case wind angle is a headwind. Because even though you get the benefit of a tailwind on the like downwind legs, the like detriment on the upwind legs is still too much that it decreases your overall lap time. And so we usually set wind angle to 0. And then V wind we usually set based on where we're going. So we usually go to like weather spark or something. And since we're going to be flying, we're pretending we're going to be flying in San Luis Obispo. We can go here, and let's say we're going to be flying on like June 5th. Let's say just the end of the quarter. You can find like the temperature, which is important for the density and stuff. And you can find I think this has the wind. Yeah, wind speed. So like 13.8 miles per hour, and you can just use that value. But for like Tucson, for example, it ends up getting actually very windy there. And so it's a pretty important thing to consider. Like if you have 22-mile-an-hour winds, like you're going to want to design for that and not think that you're going to do way better than you actually are. But yeah, so that's what this code does. The actual top speed calculation is pretty much exactly what we were talking about on Thursday. So you've got that, you calculate your dynamic pressure, and then you have this parabolic drag polar function, which is your CD naught plus 1 over pi EAR, and then that all times the square of your lift coefficient. And then this just it uses F0 to find where the specific excess power is 0, right? And that's that value that we talked about when you divide everything over by the weight, basically, you get your specific excess power. And so that's why we can just use the wing loading and power loading and don't have to like use wing area and power and weight as like separate parameters. Yeah, any questions on that? On like how this code works? We went over most of it on Thursday, but if you want me to go over it again briefly, I can talk about it in more detail.
Yeah, could you like provide just like a brief summary of like what we're doing with this code? I wasn't there on Thursday, so I kind of missed that.
No worries. Yeah, here. So let me. Okay. So for this code in particular, what you're doing is you're inputting a wing loading and a power loading, and you want to see how fast the airplane can fly, right? So we know that the power is the drag times the velocity. And we know that the drag is 1/2 rho v squared times the drag coefficient times the wing area. So it's a D, not a P, sorry. That's awful. Let me fix that. Yeah, okay. We also know that our drag coefficient can be modeled fairly simplistically, but also fairly accurately as your coefficient of parasitic drag, your CD naught, plus 1/pi times your Oswald efficiency times your aspect ratio. And then again, this Oswald efficiency is how close to an elliptical lift distribution. So theoretically, the ideal lift distribution is if you're looking at your plane from the front, right, front view, then your ideal lift distribution is a perfect ellipse like this. Sorry, perfect ellipse in air quotes with my god-awful drawing skills. And your Oswald efficiency is essentially if you have a realistic lift distribution, right? Which, I mean, again, you have like a fuselage and stuff, so it's going to look something more like this, right? Your Oswald efficiency is like how close to that ideal you are.
Okay.
And we usually assume a value between like 0.65 and 0.85. 0.85 would be pretty high. But we usually just kind of assume a value for that because we can't know it without more rigorous testing. And using AVL, we can get some idea for it, which Jake will talk about in a couple weeks. But yeah, and then this aspect ratio is for a rectangular wing, it is the ratio of your span B to your chord C. And what you can see is that this also equals, if I rearrange this correctly, it should be C over C squared. Is that helpful? I feel like that's not helpful. Yo, Jake, are you here right now? Yeah, you are. Jake, what's the helpful rearrangement of the aspect ratio formula that gets it in terms of like wing area and span? You can do that, right?
Google time.
Yeah, fair enough. Oh, I'm dumb. I think it's just B squared over S. Yeah, sorry.
Sounds right.
So what you can see is if you multiply by B on the top and bottom, you get B squared over BC. And then B times C is just your wing area. So B squared over S. And that's useful because that gives us like a general formula for if we don't have a rectangular wing, if we have something like one of the wing shapes Jake was talking about on Saturday, right? But we know our wing area S, and we know our span B, then we can still find our aspect ratio using this formula. For this case, like most of the code, well, I guess you can play with the code to get whatever wing geometry you want. But yeah.
Okay.
So yeah, so basically then we can sorry, basically I've said that like 3 times.
So,
yeah.
So the code is to help us find a more ideal wing shape or airfoil shape.
No, sorry. So that's for later. This was just kind of a tangent about aspect ratio. My bad.
Oh, okay.
Yeah, the main purpose of the code is ultimately going to be to select your wing area, your takeoff weight, and your power. Those are the 3 main parameters that I want you guys to get out of this. You'll probably want to select a wing shape going in, just because it'll make it easier to manipulate some of the parameters and stuff.
Yeah.
But as far as yeah, as far as this code, these are the main outputs that you're looking for today.
Okay.
And so the way we do that is by basically plugging this formula. Oh, I guess I should add one more line of formulas, which is that your CL equals your lift over 1/2 rho v squared times your wing area. And then since your lift equals your weight, right, in steady level flight, if you weren't here on Thursday, God, I can't draw. Thrust, drag, lift, weight. And so lift equals weight in steady level. And so that's going to be your takeoff weight over 1/2 rho v squared s, which this weight over wing area is your wing loading. And that gets to the next point of why we want to deal with wing loading and power loading. So what we can do is we can say your wing loading over 1/2 rho v squared. And then we can plug this into here. Then we can plug this into here and this into here. And we get a big ugly formula. And then when we divide everything by weight, we get a power to weight ratio out here. We get a 1 over the wing loading here. And then we already have a 1 over wing loading in this. And that's what this code is, right? So if you look at what's going on here, it's saying this is 1/2 rho v squared. It's just calling that Q for the dynamic pressure. Then it's calculating the CL as like the wing loading over the dynamic pressure. In this case, N and beta are both 1, so you can ignore them for now, right? So you have the wing loading over the dynamic pressure. Then you've got this drag polar, which is that CL squared over pi EAR plus your CD naught. And then instead of having what I have over here, which is like power to weight equals this stuff. So right now I have like power to weight equals dV over W, right? I'm going to subtract this over. So I'm going to say 0 equals, I guess I'm going to subtract this over here. So I'm going to have 0 equals power to weight minus dV over W. And I'm going to find the velocity for which this is true. And that velocity is going to be the speed at which your aircraft flies with all of these input parameters, right? Any questions on that from anyone? Matisse, did that answer your question?
Yeah, that made a lot more sense.
Okay, cool.
Thank you.
For the time being, I want you guys all to ignore engine deck row. I don't know what it does, if I'm honest. It's very strange. I legit, I think it just, anyway, this alpha parameter that it outputs is essentially your propulsive efficiency and a loss term that comes from the fact that we're not flying at sea level. Yeah, that's all I've got. So you do just want to treat it kind of as like your propulsive efficiency. In some of my code that I've done after this, I just gotten rid of that term, but I haven't made that code good enough to share with the world yet. So for now, we're just using the existing code. Yeah. Also, I should probably note that propulsive efficiency is basically getting multiplied in here, because that power is going to be just the mechanical power, but we're really interested in the electrical power, because that's what tells us how long our aircraft can like stay in the sky. Is if we're drawing too many watts, then our aircraft is only gonna drain the battery too quickly. And so we really care about that propulsive power, not the mechanical power. And we have that P prop times eta is P mechanical. And eta is that propulsive efficiency. And that's also something that we just kind of assume based on the past. One of the things I'm working on is trying to get a better way to work with that, but for now we can just assume that it's like 50% efficient. Yeah, okay, so that's VTOP. The next part of this lap calc code is max turn, or max turn rate parabolic. And that does almost exactly the same thing, except instead of like trying to find the velocity at which the instead of trying to find the velocity at which the specific excess power is 0, it sets the lift coefficient, and then it tries to find the load factor where the specific excess power is 0. Because this turn is not steady level. In a turn, instead of thrust, drag, lift, weight, we actually have like a much more complicated situation. But in essence, we can say that instead of the lift being equal to the weight, in a turn, or steady level flight, we have lift equals weight. In a turn, we have lift equals a load factor times the weight. And so we want to find the load factor that basically keeps this specific excess power 0. And so our velocity will actually fall out of that as like a byproduct. It's not what we're most interested in. What we're most interested in is how quickly is like the angular rate of our turn. Because we know that our turn is 180 degrees in our lap. And then there's one 360-degree turn in the middle. So if we know, like, oh, we turn at 10 degrees per second, we know that our turn is going to take 18 seconds. And that's what we're interested in, and that's what we can get out of this turn rate code. It's not great turn code. It assumes steady turns, which is kind of a bad assumption. But it's what we have. Jake and I are working on making better turn code this quarter. But for now, you guys can just use that. Yeah, and then this wind calc basically just subtracts the wind speed from your airspeed on one leg and adds it on the other leg to find your actual like ground time, and then plus your turn time, and then that calculates your total lap time. And so that's what this code does. And so in our sample script, here I have a bunch of variables. So I've set the air density, I've set the propulsive efficiency, parasitic drag, Oswald efficiency, aspect ratio, CL turn, CL takeoff, or I'll get to that in a second. Your wind velocity, your wind angle, etc. You will probably, for some of these, not want to set them outside. Like you might want to not have your aspect ratio fixed at 5 or fix at anything. You might want to iteratively calculate it based on something, and I'll get to that in a second. But yeah, so that's the lap calc. Any questions on the lap calc function? All right. DBF takeoff is a very simple function. It's experimentally verified, which means that it doesn't really represent anything legit. It's just, it works. You can calculate this takeoff parameter using your wing loading and your power loading, which are called different things in this code. But don't worry about it. It's the same thing. Again, that propulsive efficiency, which is your alpha term, and then your CL max. And then these A and B were found just by testing a bunch of different planes and trying to see how they take off. Or rather, testing one plane a bunch of different times, which is probably not the way to do it, but whatever. Theoretically, this calculates your takeoff distance. And so that's where, sorry, sample script. That's what I use this like CL takeoff for. Again, if you guys are thinking about doing high lift devices, you might want to incorporate that into the CL takeoff term. And then that code wants an altitude instead of a density. Not sure why. It just then uses that altitude to calculate the air density. So I just have that input separate from that. Any questions on the takeoff code? All right. The last one that I want to show you guys in particular is this weight estimate. A whole bunch of different people worked on different parts of this code. So it's kind of messy, but it works pretty well. The big thing for this code is that you do need to input a takeoff weight. You can't just put in a wing loading and a power loading. And so I'm going to suggest that you, well, when I get to actually creating a score function, you will probably want to, at each wing loading and power loading, you can calculate the other stuff. You can calculate the like lap time and the takeoff distance and stuff. But to actually calculate this empty weight, you're probably going to want to iterate through a bunch of takeoff weights and then pick the best one, right? But for this sample code, I just set the takeoff weight and the span and the load factor and stuff. This TC is your airfoil thickness as a fraction of your chord. 0.098 is a good guess. Once you have a more detailed design, you can set it to that. But for now, it doesn't really, I don't want to say it doesn't matter, but because you haven't picked an airfoil yet, and that's more for preliminary design, just putting whatever value there is going to be fine. It'll still tell you a good optimum. And then you can go for like actual more detailed performance calcs. You can go and change that once you have your airfoil thickness. Yeah, also this just creates a bunch of vectors, like arrays with your different wing loadings and power loadings. And then this stuff cleans up your data a little bit. Because if you have a super low, or I guess if you have like super low like wing loading or power loading, for example, you end up getting like really, really high lap times. And you only have 5 minutes to fly 3 laps. And so any laps greater than 100 seconds are going to exceed your flight window. And so that just cleans up some of the data, gets rid of those asymptotes near 0. And then anything greater than 50 feet, you can't do that for takeoff. And so this gets rid of all of those. And then you can do contour plots, wing loading, power loading, top speed, wing loading, power loading, takeoff distance, wing loading, power loading, empty weight. The rest of the syntax is pretty straightforward. This C label is just what makes it put the actual numbers here. If you don't have that, it doesn't put the numbers. Numbers are usually helpful, unless you're just trying to get a qualitative like picture of how it goes. Yeah, that's this code. Any thoughts on this?
Sounds like a complicated code to write.
Indeed, I did not have to do a lot of the legwork on this. I will say I didn't use all of it in the same way this year. We can talk about that more a different time. This year, I kind of need to sit down and like do a postmortem on scoring analysis this year because I had some ideas at the beginning that kind of fucked me over. So that's kind of why I'm going back to the old code that other people have written. And as I said, like a lot of this stuff was written collaboratively with like a whole bunch of people. And so
And just to clarify, we're going to use this code?
Yeah. This is the code I want you guys to use. I don't trust my code enough to present it as valid. So
will we ever throughout the quarter make our own code for anything?
You are absolutely welcome to. And in fact, so this is not enough to pick a design, right? And that's what I was getting to next is this code, it calculates performance, but it doesn't help you do anything, right? So what it's going to be on you guys to do, and that's kind of what I want you guys to do today, because this is it. This is the end of my talking time. What I want you guys to do is try to figure out and try to actually make a function or a series of functions that'll let you calculate the score as a function of wing loading and power loading, right? So all of these tell you, like, you can figure out how fast it flies, how quickly it takes off, how heavy it's going to be if you have a good way to put in a weight, right? But it doesn't tell you the score. It doesn't tell you which is going to be the best design. You have a constraint diagram. You can use a constraint diagram. You can plot a bunch of different constraints. You can say like, ooh, what if instead of 12 feet, we wanted to constrain it to like half a foot? Then you do that. And you see that it's this kind of crazy, you have to have a super high power for a pretty low weight or just a massive wing or something. And so you're like, okay, maybe that's not doable, but maybe it is, right? Like that's kind of on you guys to figure out. This is just the tools that I'm giving you to try to find an optimum design point. Yeah. So I guess with that, I'm going to turn it over to you guys. You guys all have the code. I sent it in the Slack. It's a zip file. The sample script is in the first folder, and then that sample script automatically like calls a second folder that has all of those performance functions. And see what you guys can do. Like,
Hey, question.
Yeah, what's up?
If we really don't like coding at all, do we have to open up the? Because I'm lost. Like any coding I do is I'm just like totally completely lost in. Can I just like be part of the design instead of the actual like hard math part?
You're welcome to do whatever you want.
Okay.
What I would say is something like DBF is a good place to get practice with the coding.
Okay.
Like I learned MATLAB through DBF before I ever took a class on it.
Okay.
And that was my first coding language. Like I had never programmed anything before. But now it's like such a crucial part of just like, not even like assignments that make you do it, but all assignments. Like it's so much easier to make a function that does it for you and then never have to think about it again.
Right.
As opposed to just like, you know, grinding through a bunch of hand calcs all the time.
Okay. Okay.
So it's up to you. Personally, I would recommend using this as an opportunity to get familiar with it.
Okay.
But if you really don't want to, like, you're not forced to at all.
All right. Sounds good.
And
where'd you say it is?
It's in the Slack.
Okay. Cool.
I sent a zip file in there.
Cool.
In the general or the mock comp?
In the mock comp. Yeah, I sent it on Friday.
Okay. Oh yeah.
Also, if you, because I know there are like some freshmen in here, if you are in a position of like having no coding experience, you're not expected to yet for sure. So if you want to just like get used to MATLAB and not be diving into like the most intense stuff that we do in this whole club, there's like resources that you can use to just learn MATLAB. And honestly, those are just as good a use of your time as doing this stuff right now if you're at that place. So if you need to learn MATLAB, like we can point you towards that, those resources, because you don't even start, like there are definitely classes where you do a ton of like coding related stuff, but you start off with like more introductory stuff like at the end of your second year, so, or beginning of second year, and then the more hardcore stuff comes at like the end of second year, beginning of third year.
Yeah, I just sent in the Slack a link to MATLAB on-ramp. Those of you in Aero 300 will be familiar with this. I think they have you do it in the first week of lab.
Yeah, we just did it.
Okay, cool. So for the freshmen, if you guys want to go through that, you're welcome to. It is 2 hours, so I would probably recommend doing that after the meeting. But yeah, that's a good external intro to this as well. Gets you familiar with like the syntax and the basics of it as well. So, and then also like, if you have MATLAB questions, I can totally answer them, or at least I can try my best. Yeah, so I'm always there like for that as well.
If you haven't used MATLAB before, but you have programmed in other languages and MATLAB just looks weird, it is a little weird, but it's honestly like one of the most straightforward languages to learn because it's very user readable. So you should be able to pick it up pretty quickly. But if you haven't programmed at all, then like this is obviously a big jump. So it's not like, it doesn't reflect poorly on you that you're like, I have no idea what any of this means.
Yeah, all of that.
Wait, you said if we ran the sample script, it should open everything in the folder?
Mm-hmm.
It just gives me errors that doesn't recognize the functions.
Do you mind sharing your screen?
Sure.
It says just download like a aerospace toolbox, which is like an add-on.
You shouldn't need to. Unless I
Laird, have you been using illegal functions again?
I don't think so. Okay.
Yeah.
I see the problem. Okay, so go to or hit run really fast. Okay. So you're in the wrong folder is I think what's happening here, unless you put this in your lab 2 data folder. So go to yeah, I'm trying to so on the left you have your current folder.
Oh, okay. So I just changed my current folder.
And yeah, if you hit the one of those buttons, yeah, you should be able to reset it.
What each of them do? Maybe that one. Nah.
Can you go to where?
There you go. Just go to downloads and then yeah. Yep, that's the one. Okay, and so then you're gonna want to so it will automatically add that to path now that you're there. So if you hit run now, it should work. Conv length requires aerospace toolbox. Grr, okay.
That is correct.
What does that mean?
Okay, but it's probably worth it to get the Aero toolbox because it's pretty great.
I would just get the
Yeah.
Aero toolbox if I'm honest.
I tried getting it and it said that my MATLAB administrator has restricted access to Aero toolbox.
What?
Uh-oh. I'm gonna check.
What?
That's some BS, dog.
That's some BS, dog.
There's a bunch of functions called conv and then a unit, and they're a really easy way to convert between a whole bunch of units, and they're in the aerospace toolbox because aerospace is the only field where we use like all the units all the time from both systems. But we've always been able to get whatever toolboxes if we wanted them, so I don't know
Yeah,
why they would be restricting you.
Peter, do you have it through Cal Poly or do you have it from something else?
I got it through Cal Poly. I'm using my
Okay.
Cal Poly email. This is MATLAB our 2020B academic
Yeah.
use.
Huh. And so if you go here, let me just
Don't
Okay.
pirate the aerospace toolbox.
you really shouldn't need to. So if you go to home and go to add-ons,
Okay.
and then search for aerospace toolbox.
Hold up. Where's that on?
In your home tab, it's like
Oh yeah.
right there. Yeah.
Yeah.
And search for that.
Hmm.
It should be the first result, and then try downloading it that way.
Yeah, that's how this is the page I think I got to.
Really? And it didn't. That's bizarre.
It's installing for me.
Okay.
What?
Peter, can you try just like closing MATLAB and reopening it? Or I don't know.
I'll try it.
If that doesn't work,
You could
No, we
also
got it
try
later.
requesting a new license from the school and
Yeah, but that's a
relinking your license
pain in the ass.
as like step 4 or 5.
Yeah.
Okay, it works now. I
Cool.
didn't even
Good
do it.
job.
I love this.
Love that.
Yes. Welcome
I
to
changed 0
enterprise
things.
technology.
So the sample script is just supposed to, what's it supposed to do?
The sample script is just what I've shown here. So all it does is like shows you what is possible. Oh. Were you guys even able to see when I was like in the store or whatever?
Not the store.
Oh, whatever. Okay. I was just sharing my one window. My bad. But yeah. So this sample script just generates these plots. So it just shows you that you can calculate top speed at all of these wing loadings and power loadings.
I also have an error when trying to run it.
Okay. Can you share your screen?
Yeah.
Okay, are you running this inside the zip?
Maybe not.
Okay. Can you just double click that? Yeah. Now try running it. Change folder. There you go. Nope. What on earth?
The folder got changed.
It did.
There's no
It
folder
did.
there now.
Can you show me where you saved the file?
Yeah.
Like just in your file explorer or whatever.
Okay, I have to head out now, Laird.
All right, see you, Johnny.
Yeah, have a good night, everyone.
See ya.
Bye, Johnny.
Oh, do I have to change what is being shared, or can you see my?
No,
file?
I can see it. I can see it.